GDG Cloud Boston and GDG Atlanta are pleased to present formal session number 5 in a series of 12 meetings for the Professional Cloud Database Engineer Certification Workshops. I'm your host, Norbert Kremer at GDG Cloud Boston. Joining me as co-host is Jessica Rudd at GDG Atlanta. All of our GDG meetings are covered by a code of conduct. The spirit of that is very simple. It's just be nice, respectful, collaborative, and participate to the extent that you're able. And the formal version of that is here. If you want to read all the legal terms, that's fine. The slides will be published later, so you don't have to make sure you don't have to get any of these links. They'll be in the slide deck later for you to click on. That goes throughout this whole deck. There's quite a few links here today. Few housekeeping notes. Normally we do record the sessions and we post them to YouTube as quickly as we can. We did not post the last 2 weeks. 2 weeks ago we had a guest speaker join us who did not wish to be recorded, and we had kind of a free-for-all discussion, and so we're not able to record that one. And last week I was busy at a conference and Jessica was hosting. We thought we were going to be able to record that session. We were not able to because of a technical problem, actually with permissions. And so this week we're back on track. We'll be posting this to YouTube, and we'll post also the link to the slide deck as well. And at the end of the workshop series, Jessica has been working on a Google Doc, which has a lot of links to a lot of the important documents that we're mentioning throughout the series, and that'll be put to a permanent location because of our Slack channel will go away after 90 days because we have the free version of Slack. Finally, to get Skills Boost access, you do have to actually register for a meeting and also actually join a meeting to get the Skills Boost access. I think the Skills Boost turned over at the end of the month. I noticed at the beginning of August, I got another email from Google, and I believe that was because it turns over monthly and we got a renewal for the access. I have a checkpoint set at 7 so that we don't run over. We'll make every effort to stop at 8 today. I do have a lot of material today, as you'll see. And we'll stop at 8, give or take a minute or two. And if there's anything left over, we'll carry it into next week. We are getting into the end of the series here. We have today, and we have an informal session next week. And then for our last session, August 27th, we're calling that the grand finale. So we'll give some pointers on exam prep, and we'll have some swag to give away, and we're going to have someone else, Uyanga from GDG Cloud Boston, is going to actually record that session, and we're going to make a video out of that, a short video that we can use to promote these events. We think these are great events in the Road to Google Developer Certification program, and we're working with Google to publicize these, and we'll probably have additional ones running throughout this coming year. Okay, with that, oops, I didn't fix this. We're not having guest speaker presentation. That's a mistake. So we're just going to go into reviewing the last weeks, and then so we're in week 9 now of our 11-week. The counting is 12 weeks, so it goes 0 to 11. So we're in week 9 of 11, but it's a zero-based counting system. And then we'll have content review, Q&A, and then looking forward to the next steps of how we wrap up the whole series. Okay, so review of the last few weeks. I meant to present a lot of this material 2 weeks ago. I prepared this, and then when our guest speaker, Walter Lee, became available, we decided to give him the majority of our time. And so this material got pushed into today. Now, I do want to point out something that appeared in the news on August 2nd is that there's now a SQL interface on a so-called NoSQL database. Okay, so Bigtable which you've been working with in your courses, has now acquired a SQL interface, which is really interesting. And I'll explain why this is a good thing. However, it also just underscores how silly the name NoSQL is, and I'll have more to say on that. But I just thought I'd point this out as it was a newsworthy event relating to a Google product that we've been working with. I gave you the source there. That's green source there. At the bottom is a clickable link, so you can explore that later on. I do want to go into what I consider the key concepts for this whole workshop series. If you must learn these basic things to consider to meet my criterion for completing this series. And also, if I were a hiring manager and I were interviewing you and you messed up any of these basic concepts, you'd be out immediately. And so these are critically important. It is astonishing to me how many people get these basic ideas wrong. And I will give you a number of examples that I think are appalling. And so I beg you not to make the mistakes that I'm going to show to you, and please come back to this particular slide. Make sure you have all this really, really down solid. It's not that hard. It really should be something you can learn in an hour, and people just repeatedly get it wrong time after time after time. And I'm just astonished and embarrassed that that's the case in our field. So there is a bit of a problem I want to go into. So first of all, let's start with SQL. You can pronounce it. It's properly called SQL. I will use the word SQL, as do most people. The point is, SQL is structured query language, stands for structured query language. And it is a query language, okay? It is not a DBMS. It is not Microsoft SQL Server. It is not equal to relational databases. It is a query language. The data storage that underlies the database system determines whether it's relational or non-relational. That is independent of which query language is being used. And so today it is true that most relational databases, I would say even almost all relational databases, use SQL as their query language, but that was not always the case, and certainly not in the beginning. It was not established that way. The relational model and the SQL query language were developed somewhat independently, and it was not a foregone conclusion in the beginning that SQL would become as common as it is now. So just be clear, in particular when you say, oh, I'm using SQL to store my data, or I built a web app with SQL. That, most people, when they say that, they're talking about Microsoft SQL Server. That's a mistake. Please don't get that wrong. Don't mix it up. Okay, the next point, a relational data model or a relational database. What does that mean? It means that in column 2, the data is normalized into relations. Relation is a mathematical term that comes out of set theory. It's the theory that Ted Codd used to build this data model in the late 70s or in the 70s. And think of it this way, a relation in our practical world of database practitioners, a relation is simply a table or a view. It has a precise mathematical definition. That doesn't really matter for us right now. For us, a relation is a table and a view. That's the language that Postgres uses. You'll see that in many, many places. It is not directly related to the idea that there are relationships between tables, that is foreign key and primary key relationships. That's not what relation means. That's not what relational means. Relation is a mathematical term. It stands for a table or a view, okay? When we have relational DBMS, right, relational database management system, we typically normalize data into multiple tables, and we join the tables back together. And we also have so-called ACID transactions that mean minimize the data inconsistencies that we might otherwise get. That's what this system is built for, is to maximize data integrity and give us a lot of flexibility in the way we ask queries of our data. It does not, over in the third column, relational database does not require the use of SQL. Although that's the most common thing today, it was not always true, and it need not be true. There are other query languages that could be used against a relational database. Relational database has to do with the way the data is stored and organized into tables. Okay, let's go to the next row, and you'll get to the point after a while that I'm obsessed with these ideas, and they're critically important. And when you see the number of mistakes that people have made in the trade press and elsewhere, you'll be astonished, and you'll then begin to understand why I'm so obsessed with these ideas. A row-oriented database, or a row store, is the traditional relational DBMS that we had throughout the 70s and 80s and 90s. Okay, all the values in a row, meaning a row could also be called a tuple or a tuple. The values in a row-oriented database are stored in adjacent physical locations. Okay, so that is a write-optimized database that is suitable for OLTP applications. Normally we have small inserts, small updates, and small deletes. And when we query, we also are usually retrieving back a fairly small number of rows, or maybe even a single row. This is a kind of relational database because the data is stored in tables that are typically normalized. Okay, let's go to the next one. Column-oriented database, or also called column store, or C-store, or columnar database, with Vertica being one of the first commercial products that really popularized this. It's strictly not the first commercial. I should update the slide. It's strictly speaking not the first commercial product that had column store, but it was the one that made this data model prominent. It is a relational database by definition because the data are organized in tables and you join them together. So you could have a star schema with a fact table and dimensions. You would do joins to retrieve the data that you want, get the results that you want. Just because it is column oriented does not make it non-relational or NoSQL. It's just simply not true, and it's something that a lot of people mess up. So finally, I want to get to the column family, or wide column type of data storage, of which the great examples are Bigtable and Apache HBase. And you've been working with Bigtable, so you have some familiarity with what that is. So it's a key value store where the value is a group of predefined column families. So this is now a kind of non-relational data store, badly called NoSQL, poorly named NoSQL. It's really should be called properly non-relational data store. Okay, what are the features of Bigtable? It has simultaneous high write and read rates, horizontal scaling. Each row may have a different set of columns. That's a little strange, takes some getting used to that, and the other feature is it does not have ACID compliance in the way that the other relational databases do, and it also doesn't support joins. So there's only one column, the row key that is able to be used, that has any index on it, right? So that's the only one that will give you any kind of decent performance when you're doing a query, and it doesn't natively have any way to do a join across different tables or different rows. And in fact, different tables is kind of a stretch even in that. So let me leave it there. I think you have the idea of it, and thank you for bearing with me as I go through this in a lot of detail. I want to give you the examples here of what do I mean by row-oriented? What's the data orientation? This is straight from Wikipedia. There's examples from Wikipedia. On the right side, you have that data orientation link there. You can read about the details. But if we have, as shown on the left side, 2 rows of data in a table, and it's organized in the normal way, column 1, column 2, column 3, and we have item 11, 12, 13 in one row, we have item 21, 22, 23 in the second row. When they're organized on the disk, when they're laid out on the disk, item 11, 12, 13 are adjacent to each other, just as they are in the logical table on the left. So if you look at the bottom on the right, the physical layout is exactly the way the row is laid out in the logical table. And then when the third column is stored, it picks up with the next row. And again, there are 3 cells like adjacent to each other physically. Okay, let's look at now the column-oriented or data orientation in a column store, C-store, column-oriented databases. These are synonyms. And I'll tell you in a moment which terms I prefer so that you can avoid confusion. Okay, but for now, let's call this column-oriented database. That's one of the words that the original authors used. So that's a completely good term for this type of database. But the point is, we have the same data in the left side. We have the same 2 rows of data, right, logically. But how are they stored physically? Well, 11 and 21 are stored adjacent to each other in the down on the bottom right. 11 and 21, 12 and 22 are then the next ones laid out on the disk. 13 and 23 then follow from left to right as the layout is organized on the disk. So you see that it goes column by column, whereas previously we had row by row. That's the fundamental difference. This is kind of a schematic layout. I'm not sure that it would really physically be exactly like this on the disk, but this is the basic idea of it. What does that let us do? We get better compression because all of the data elements of this, all the data elements in one column are of the same data type. Okay, that's by definition of relational model. Everything in a column is the same data type. By having all the same data type elements stored adjacent to each other, you can apply much more efficient compression techniques than you can with a row store, where you have to kind of compress a row on a row basis, and you have to deal with varying data types. So some of the compression techniques that are available in a column store are things like run length encoding and dictionary encoding. You'll see these terms. It's too much for us to go into in detail right now, but when you see terms like that, those are techniques that are more easily applied to vertically oriented, column-oriented data rather than row-oriented data. So, okay, when we have also, along with a better compression, we can make use of vectorized operations in the database to do calculations. A lot of data warehouse queries, analytical queries, for example, require filtering and aggregation. Aggregation in particular means summing and counting and getting the min and max. A lot like average, a lot of these calculations can be done much more efficiently in a vectorized fashion, and that's done in multiple layers of software, including all the way down at the chip level, where you have vectorization operating actually in the CPU itself. So that is really helpful for a lot of things. Also, sometimes analytic queries don't require every column to be pulled back. If you, for example, get the average salary of the employees, right? You're just going after the salary column. You can skip all the other columns, and therefore that having all the column data adjacent to each other and separate from the other columns makes it much more efficient to do that kind of analytic query. Whereas if that were stored in a row store, you probably would have to pull back all of the row data, even if you only needed 1 or 2 columns or a few columns. Those are the fundamental advantages of column orientation. Now, let me go, I want to go into the amount of confusion that exists in the field, in the trade press. I'm going to give you 6 examples. Let me just ask you one question. Do you think that these 2 programming languages, which have similar names, right, do you think they're the same? Is Java the same as JavaScript? Are they at all similar? I would say not really. they're wildly different, in my opinion. But they do both start with the word Java, right? J-A-V-A. So they must be, therefore, people mix them up all the time? No, not really. I don't think so. However, when you get to Vertica is a column store or C store, Apache HBase is a column family or wide column. Are these the same? Well, of course not. They're not. They're really very, very different, as I've just spent a few minutes explaining, right? They have different data layouts. They're used for different purposes. Oh, they're both databases that have rows and columns. I mean, they have tables that have rows and columns, so in that way they're similar, just like Java and JavaScript are programming languages, but they're actually very, very different. However, AWS, and I'm going to pick on, not picking particularly on AWS, except that they happen to get it wrong, and I wasn't actually searching for these. I've just, in preparing the notes for this presentation, I found many examples of this basic concept being misstated, right? Okay, so a column-oriented database doesn't say whether, well, a column-oriented database like Vertica is actually relational, right? It's not just column orientation doesn't make it non-relational. And the first half of the sentence is incorrect. HBase is column oriented. That's just flat wrong. HBase is a column family database, which is a non-relational database. So if they got the first half, if they corrected the first half, then the second half of the sentence would actually be correct. But the first half, the first clause in the sentence is actually completely wrong. HBase is not column oriented. It just isn't. And I'll show you why in a moment. So Amazon got it wrong in their documentation. Datanami, which is a respected trade journal in the database field, also got it wrong. Columnar database, the family of NoSQL database, Bigtable, Cassandra, HBase. So far, that's correct. Is similar to document store? Yeah, maybe, but they're not columnar. The problem is the family of NoSQL data. The sentence doesn't match the phrase that's in bold, the headline in bold. Columnar data, but those are not columnar databases. Those are column family databases. The examples. Okay, so that's where that's wrong. Also, and then, however, this is actually referring to a paper from Mike Stonebraker that was released in I think about a month ago. And so don't believe the big database hype Stonebraker warns. I'll give you the reference. I'll bring up the paper in a moment and give you the reference to it. But for now, I just want to say that, Datanami got this wrong. And then secondly, the second sentence, however, the column store family already is obsolete, also completely wrong. Column store family, column stores are BigQuery, Redshift, Oracle Autonomous Warehouse, Teradata, and a number of others that I could name. These all use column store, so it's definitely not obsolete. It is the best model for the reasons I just described. Okay, because of the compression and all that. So let's see what did Stonebraker say? Stonebraker and Pavlo. This is a paper called "What Comes Around Goes Around." Well, I'm sorry. This paper, what goes around comes around and around. It's kind of a joking, somewhat whimsical reference to an earlier paper written about 15, 20 years ago, I think. It's called "What Goes Around Comes Around," period. And now they've added another round of around at the end, just as another review of comparing relational databases to so-called NoSQL databases. So what did the authors actually say? They said very clearly next to the red arrow, despite its name, column family is not a columnar data model, okay? So in other words, Bigtable and HBase and Cassandra are column family or wide column databases. They're not the same as columnar data model. So that's from Stonebraker directly in this paper. Okay. Now the other thing which I think is maybe not completely wrong, but inaccurately stated in this Datanami thing is that even if you correct and you say, okay, when they said column store family is obsolete, let's give them benefit of the doubt, correct that. What they really meant to say is, however, the column family group of databases is obsolete, and without Google, this paper would not be talking about this category. Now, there is a reference in there. Yes, without Google, this paper would not be talking about this category. But what Stonebraker and Pavlo actually say is that column family systems are a niche market. They don't say it's obsolete. They say it's a niche market. That's a big difference. And as I pointed out on the right, Google's still using Bigtable for search and Gmail and has 10 to the 19th bytes stored in Bigtable. So it's not going away anytime soon. I wouldn't say it's obsolete. It is a niche market that probably Google uses it more than anyone else. Probably Google has more in Bigtable than all the rest of the world has in Apache HBase. It is not obsolete. It is a niche product. And so this is a complete mischaracterization. It's both errors and mischaracterization of what Stonebraker said, okay? So let me go on the menu. TechTarget, also a mostly reasonably good source of information on cloud and databases, also said NoSQL database types explained, column-oriented databases. Again, equating column-oriented with NoSQL. In other words, mixing column-oriented and column family as if they're the same thing. And I hope you got the point by now that they're different. Okay. And then as I don't give the names of the authors. You can click on the links if you want to. I'm not trying to embarrass the author, but this author in particular demonstrated a thorough lack of knowledge in this subject area throughout the rest of the article. It is an abominable piece of journalism. And I often go on about how bad the trade press is. This is a great example of it. And I'm talking about in cloud in general, multi-cloud is this, and all the trends that are happening, and everyone's upset about their cloud overspending, et cetera, et cetera. A lot of these trade press articles are just, I find, really, really inaccurate. And in this case, they're just completely wrong, okay, and demonstrably so. Okay, now you would say that, gee, it's really hard to be an expert on this. You have to go to MIT and get a Ph.D. from Stonebraker before you know this. Well, no, that's not true, because the books I quoted a few weeks back, in fact, this one that is about Stonebraker that celebrates his getting the Turing Award, it has, from the index, it mentions only column-oriented and column store. It doesn't mention column family at all, because Stonebraker is primarily, his whole career has been largely about relational databases and other types of powerful database systems. He's not typically a big fan of the so-called NoSQL data stores, non-relational data stores. And so it doesn't even appear in the index. Likewise, in the book, another book that I mentioned a couple of weeks back, the NoSQL Distilled book from Sadalage and Fowler, excellent authors, by the way, they don't mention the word columnar or column store anywhere in the book, but they do talk a lot about column family databases, of which Apache HBase and Google Bigtable are the prime examples. Okay, so yeah, if you read these books, you would not probably confuse these concepts. And then again, if you don't want to buy the books, you can just do a Google search and click on a couple of links, and you get the original ideas from the authors themselves who made these things very popular. Okay, query execution. The top one is from Abadi, from Daniel Abadi, who was a student of Stonebraker when they developed C-Store, column store. C-Store is a column-oriented DBMS. It's the research of that paper that went into developing the Vertica product. Okay, so it's like real, and the paper, believe me, the paper is, even if you're not an expert, you're not a database expert, you can easily read these papers and get the main idea from it. They're very clearly written, and they have, like, even if you just look at the pictures, just look at a high level of the pictures, and you can see kind of the architecture of these systems, and it just look really clear. It is not anything that would lead you to be confused about any of this. And then finally, at the bottom, we have from Jeffrey Dean and his group, we have the Bigtable paper, which talks about tablets and the storage that goes into Bigtable. And again, does not ever call it a column store or a columnar database. It's called a column family database. I use the word, so which words do I like? I like the word column family, and I use the word columnar or column oriented for the column stores. And if you maybe don't use the word column database or columnar, the most clear word is column store or column oriented database. Those things will not get you into trouble. There are a few terms that are well defined, but actually could be ambiguous if you're not an expert. Okay, so I would recommend that just be really careful about, wide column, Kasaba, I see wide column. That is an absolutely correct term for column family, an alternative term for column family database. I personally prefer column family. I think it makes more sense as to what it fits better to my picture of the architecture, which I'm going to show you in a moment. Okay, now Wikipedia, where can you get the correct information? Okay, I've given you a bunch of places where you shouldn't look for bad and misinformation, right? Wikipedia is mostly accurate, but sometimes gets it wrong. Okay, I don't have an example of that, but Wikipedia is not perfect. Mostly correct though, mostly good. As I pointed out, many journalists and pundits just get it wrong simply because they're sloppy. Frankly, it's just sloppy journalism. They don't take the time to understand these fundamentally different systems, and they're just wrong. And I don't have a lot of patience for that because they're supposed to be educating us. They're making us look at their ads all the time. So I don't have too much patience for them getting it wrong. A major cloud vendor got it wrong, as I showed you. Guess what? LLM-based chatbots don't have a chance of being correct all the time because, first of all, they hallucinate, and second of all, there's so much bad training data that they're trained on. So how could you possibly expect an LLM-based chatbot to get it right? Okay, where can you get it right? Okay, Dama Dimbach. I pointed out the data management body of knowledge book from DAMA, the Data Management Association, which has their own certification track. They have their own big fat book to help you study. They get it right, but they don't really go into much depth on either topic. So at least it's correct as far as it goes. And TDWI, where I was teaching last week, in fact, they always get it right because I'm there, and other people like the other faculty members, we all talk to each other, and we know our stuff, and we always get it right. We never mix this two fundamentally different things. We never mix them up. Okay, so all right, let's move on to something else. if you're still listening to me, I want to go into like, what does NoSQL mean? What do we mean by NoSQL? And this is a rather humorous slide that I got from my colleague, TDWI faculty, another trainer at the conference where I was last week, Mark Matson. He's got his own independent consulting firm, as do I, and his is called Third Nature. So I got this slide from him. It's actually pretty old. It's been around for a long time. I saw this slide actually before I met Mark, and I've been meeting Mark a few times a year for the last 5 years, and he described this in a humorous way. In 1970, we had NoSQL. It wasn't invented yet. Okay, that one's easy. We had Quell before we had SQL, right? We had other query languages. There literally was no SQL. In 1980, it meant SQL was the only game in town. So if you're a database programmer, you better know SQL. 1999, this suddenly came the big data era with Hadoop and other document stores and column family stores. I want to be careful to get the words right here. Those suddenly became called NoSQL or NoSQL databases. And this is an umbrella term. It apparently got started on a blog post and went viral. And I'm going to tell you why it's not a good word. It's not, the word doesn't fit the concept. That's why I don't like the word. It's not a great word because it went viral and everybody started calling it that, including respected authors like Sadalage and Fowler. We're now stuck with this label NoSQL that actually means a lot of different things, but there we have it. That's what came from this one blog post that went viral. I don't have the link to that offhand. Then in 2005, a funny thing started happening. NoSQL began to mean not only SQL, meaning lots of databases acquired different interfaces other than the ones they were designed with at the beginning. Latest example of that is Bigtable. Google Bigtable just got a SQL interface. So now we have a NoSQL database with a SQL interface. Doesn't make a lot of sense, does it? In 2013, that's finally, we're coming around full circle. No comma SQL, meaning almost every type of data store is now beginning to have a SQL interface on it. That's not really quite true, but it's kind of a humorous situation that we have here because of this poor name. Okay, so what do I mean by it? So I think NoSQL, it's a terrible umbrella term that groups under one name systems that are actually very different from each other, and they all should have been called from the beginning non-relational data stores. So key value store, document store, all the other types of things that we call NoSQL should really all be just called non-relational data stores. And just because something uses columnar storage does not make it non-relational. Okay, so I think we got the gist of this. I want to check the time here. Okay, it's 41 minutes of this introduction here. I want to finally come back and show you now the data layout in a column family database. My preferred term is column family. If you call it wide column, I'm perfectly happy with that term also. I don't know if this diagram is too clear. It is from the Google documentation. The link is at the bottom. It's very low contrast on my screen, so I apologize for that. I probably should find a better one to replace this with. But the idea here is that the row keys on the left, that's the only column that has any kind of an index on it. So the row key, the only way you're going to get an efficient retrieval from this is by using the row key. I have two screens here. It's actually better on my lower screen. I don't know how good it is on the remote, but the row key has an index, and that's what you always use for retrieval, unless you want to do a full table scan. A full table scan on Bigtable or Apache HBase is a really bad idea. It's not. It's just not a way. It's not a way to use this effectively at all. So don't even think you should even try full table scans unless you're doing something really weird like dumping all the data out to move it somewhere else or something like that. That's different. But as far as a normal query, full table scan is out of the question. You have to use the row key. That should have come out clearly from the labs that you did, okay? Now, each row may have a different set of columns. What does that mean? Well, okay, we defined when we create the layout of the table in Bigtable, we have to define the row key and its format. We also have to define the column family. So here, column family 1, column family 2, those are baked into the structure of the table when we create that table. However, none of the columns within the column families are necessarily defined. They're not defined at table building time, table creation time. Okay, so that's a little weird. So in other words, when we first create an empty table, we have a row key, we have a format, we have an intended format of the row key, and we have column family that's going to have some, meaningful name. It's not going to be called column family 1 or 2, I hope. It's going to have a meaningful name. It could be like person and employment, something like that. It could be information about you, like where you live, your name, your date of birth, and then on the column family 2 could be where you work. Okay, so that would be a reasonable way to design some kind of a table like this. Okay, now the other thing that happens here, each cell, this is the shown on the right side with this a T1, 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 T2, T3. Those are meant to be values that are overlaid in that one cell. They have timestamps on them. So I guess a T1, 2, 3 mean the timestamps that are on those values that are in that cell. So that's very different from, that's another way that this is very different from a standard relational database. In a standard relational database, we can't modify, you can't have multiple values in one cell. If you needed to make an update, you would have to write a new row. You would either possibly delete the old row and replace it, or you would leave both rows and put a timestamp on the entire row, but you don't have timestamps on the cell level. Okay, that's another big difference here between standard relational database and this column family database. Okay, now the other thing is that all values are effectively raw byte strings. There's really very little data typing within Bigtable or Apache HBase. And the other thing that, even though you understand this now reasonably well, you may not fully appreciate until I explain this. We call this schemaless or schema on read as opposed to schema on write. We say that because we did define a very, very skeletal schema, right? The row key and the column families, the names of the column families are defined at table creation time. But beyond that, anything goes. So every row could have a different set of columns. Let's just say within column family 1, I said that's my personal information. I may not have a middle name, or I may choose not to list my middle name. So I could have first name, middle name, last name in one row, and the next row could have first name, last name. And that's perfectly fine. And there's not this idea of null that we have in relational database. So there's no null, it's just not there. And so the way to think about this is really the column name within the column family. So I'm separating the idea between column family is at the top, the blue bar at the top. Column family and column name are two different things. The columns don't, if there's no data for a particular column, like there's no middle name, it simply doesn't appear in the data for that row. There's no null, it's just not there. So the way to think about this is that the column name is really essentially part of the data itself. So you're almost storing even though this whole database overall is called key value store, right? The key is the row key. The value is everything else. All the column families make up one value. So you can think of this as a refinement of the key value store. But also at the next level down, the column within the column family is also kind of a key value pair. And you can think of both of those as almost like data elements, right? And if they're, and there's even advice given in the Google documentation, in the Bigtable documentation, that you should keep your column names short, as short as possible, because they actually are stored in every row where they appear. They're stored as part of the data. So if you have really long column names, you're going to take up more storage space, and that's a disadvantage for performance and cost, right? So it's an interesting idea that the column names actually become part of the data. Now the reason why we say this is schemaless, right? Because let's say, okay, I really want to know what the schema of this table is. Well, I could do a full table scan, right? Because we know every row could be potentially different from all the others. We could suddenly have, let's say let's say our application only captured first name and last name up until 2024, and then on the beginning of 24, we said, oh, we need to capture the middle name also. So you could say, well, up until the end of 23, the schema was first name, last name. And then suddenly the schema got changed, and it then included the middle name. So I could, by doing a full table scan, I could say, well, get all the column names in the entire table by doing a full table scan. You could do that, but 2 seconds later, somebody could insert a new row with yet another column, right? It could be like instead of just the city and state on your address, it could suddenly include the zip code, right? So that there's no constraint on whether that row can appear at any time, right? So suddenly you'd have to do another full table scan to get the schema as of that moment. And as soon as you do that and you say, oh, that's the schema for now, then another row could come in and the schema would be different again. So it really is a box of chocolates. You don't know what you're going to get until you query it. And query means a full table scan every time. And so you really, when you retrieve a row, you never know what you're going to get, and your application has to be able to handle whatever it is, right? It can't crash. It has to either process the data that's returned to it as the query result, or it has to discard whatever it doesn't like. Whatever you're not using, just throw it away. But you can't just like say, oh, I was only expecting 2 columns and I got 3, and then I therefore crashed. That's not acceptable in this data model. Okay, so that's how that works. So I hope this gives you a little more clarity on the design principles and the data layout that maybe didn't come through, even if you did all the labs here in this course. These ideas may not have come through as clearly as I've stated them here. I hope so. Hope I'm adding clarity rather than muddying the waters further. Okay, let's go on. That was my presentation of what I wanted to say. A lot of that I was going to do 2 weeks ago, and we gave our guest speaker more time. And so I rolled that in today, and then I've added some additional material this afternoon to round out these 3 types of databases that we're talking about this week. So where does that put us on our journey in overall? So again, to remind everyone, we're trying to basically go from theory to practice. I'm giving you theory that I think is important in having you understand the data structures that are in these databases. That helps you understand their performance characteristics, and it helps you know when to choose which database for which type of project or which use case. And so we're giving you theory and textbook knowledge, and that through the labs and through the exercises will give you expertise and job role excellence that you can use in your day-to-day work. And again, restating this, we're giving you enough breadth so that you know enough of all the products that are available within Google Cloud so that you choose the best technology for the given use case or for your project. And we give you enough depth to know how to use, once you choose that project, you know how to use, once you choose that product or database, type of database, you know how to use it in the best way possible. You've seen this before, so I won't go into more depth. I did this survey at the beginning of the course of the learning path. We came up with about 65 hours worth of lab and 12 hours worth of video training. We're now, at this week, we're theoretically near the end of course 8, which includes the AlloyDB. If you're not done yet, I hope you're seeing the light at the end of the tunnel. You should be able to try to wrap things up by next week. We'll have more of this review next week. We will possibly have it on the last final week also, but really the last week will be more about orienting you toward the exam. We'll probably have some more review questions, and then we're going to have our concluding ceremonies with some video recordings, I hope. So where we are today is week 9 of 11. So the 12-week workshop is called week 0 to week 11. I've only put on the so-called formal sessions on here on this page. So we're now at formal session 5, which is week 9. We should be trying to wrap up the AlloyDB course. It's okay if you're not. We still have, a good 10 days more to wrap up any of the courses that you are still working on. If you weren't able to complete all of them earlier, you could maybe have time to circle back and complete some things that you didn't get to. I know also quite a few people have joined in the middle of the series, and that's fine. It's just that you may not, if you joined last week, for example, you may not be able to catch up by next week. You probably won't be able to do the whole learning path in 2 weeks, for example. And so that's where we are. I do want to give you now the content review. These are actually the Google slides. To some extent, these are Google slides that are recommended for this point in the learning path. Google didn't actually provide slides for AlloyDB, so I made up some slides that are similar in spirit to the slides that Google provided, but let's dive into that. So we have 3 courses. We would have covered normally 6 and 7 probably 2 weeks ago or possibly last week, but because of the schedule adjustments, we're now covering this a little more formally today. So we're going to cover the 3 courses that you've been working on over the past recent weeks, right? So it's basically Spanner, Bigtable, and AlloyDB. So let me jump into the Spanner part. That this is the material that Google provides. So what is Spanner all about? We've mentioned this a few times that Spanner is okay, let's start with the basics. It is a relational DBMS because what do we mean by relational semantics? Well, fundamentally, it means data is organized in tables. Those tables have columns and rows. They're typically, the data model would be normalized, and we would often do joins to retrieve exactly the combination of data from different tables that we want. And when there's a whole normalization theory that goes along with it, that's what relational means. In practice, it means Okay, there's a predefined schema, or schema, we call schema on write. There is ACID transactions, meaning, as I explained earlier in an earlier session, if you have a group of database, let's call them, usually it's writes. If you have a group of database writes that must all happen together or none at all, that's the hallmark of ACID compliance, right? So if you, the classic example is we're moving money from one account to another in a bank, so we have to decrement one account, increment the other account. Those things must be wrapped together in a transaction to make sure that they both happen. If there's any kind of a glitch, we roll them both back and neither one happens. So we kind of make the two writes become an atomic operation, so sort of. And they're wrapped together, we call that a transaction. ACID means the specific details of that. I don't think I want to take the time to go into it unless people have questions about it. I think it's a fairly widely understood concept. There definitely are places on Wikipedia to read about it, and also I think that's been covered in the course material fairly well, so I don't want to drill into all that. The final part of relational semantics is that it uses SQL as a query language. Again, that's the common practice today. It's not a requirement. You can have a relational database that does not use SQL even today. Right, so that's the left side. On the right side, we have a horizontal scale, global strong consistency. That's kind of an amazing thing, actually. It's very important to appreciate how unusual that is. We mentioned a few weeks back that it's difficult to have two databases where both, two replicas of a single application where both replicas are accepting writes. That's pretty difficult. There are a few cases of it for MySQL and Postgres. They're often done by third-party commercial vendors. It is still a fairly challenging thing to accomplish. And so Spanner just does this beautifully across the globe with very high scalability factors and also with 5 nines availability. As I mentioned a couple weeks ago, 5 nines is actually very hard to achieve. You will not get to 5 nines without doing some special so-called HA, high availability engineering. A lot of engineering goes into getting to 5 nines. Just to give you an example, okay, that's my 7 o'clock warning. So I think we're okay on time today. 5 nines is what the landline telephones offer or offered in the past. And I don't think cell phones are definitely not 5 nines. Like if you're cruising down the highway, you still have a call dropped, once in a while. It's not as common as it used to be. It used to be, I mean, there was an ad for a long time. Can you hear me now? Can you hear me now? I mean, why is that? Why is it important to have that ad? Because cell phones were just not that reliable until fairly recently. Now they're pretty good in urban settings, right? They're still a little flaky out in the suburban areas. So 5 nines availability is pretty hard to achieve. Just as a reference point, the airline industry has approximately 6 nines reliability for a plane not crashing, okay? And airplane crashes are very rare. We just had one in Brazil, though, within the last week, right? So they do happen. They're quite rare. It's about 1 in a million flights have a crash or an episode, and that would be 6 nines, okay? Then think of cloud storage. How often is an object loss from cloud store? We call cloud storage 11 nines durability. So it's yet another 5 on top of the 6. So cloud storage is incredibly durable. And that, again, has a lot of engineering that goes into that. Okay, we won't go further on that point, but just to give you the perspective on what these 9s mean. The Spanner courses are, again, the Google slides are a little hard to read on the left here. The important points about Spanner are really just interacting with it, understanding how to load data into it. But really, there's a little bit here about defining schemas on Spanner. And you would recall the idea that I made earlier about the difference between a logical data model and a physical data model. This is what is interesting with Spanner, right? In Spanner, we have some suggestions or recommendations for a good key design, a good primary key design. And it's about avoiding hotspots in a system that is parallel, uses parallelism to a great extent. So we do want to avoid those hotspots, and there's quite a lot of recommendations from Google about how to do that by designing a good primary key. But notice that this is really a deviation from the ideal world where ideally we would just design whatever key we want that makes our application work the best, and we would do that based on the business logic that we want to achieve. And we wouldn't have to worry about the performance impact of that choice at all. But that's not the world that we live in. So there are still the physical characteristics of the databases that we use creep into the design decisions that we make. So that's why we think separately about logical design versus physical design. So we choose logically the key that we want, and then we may have to fine tune that to avoid the hotspots to get better performance. Okay, so the course, I'm not sure how deep that went. We'll have time for Q&A at in a few minutes. So if you have questions about this, hold on to that thought or put it in the chat maybe, and we'll get to it in a few minutes. Now, this is my slide. I wanted to call out specifically a few things. Again, I think these are mentioned in the labs, but they're not maybe highlighted to the extent that I want to bring them out. So I call this innovation in Cloud Spanner. So what is first of all, the top part, the true time, that's just part of what makes Spanner work. That's baked into the early versions of Spanner. The two lower bullet points, the two lowest ones, are new features that have been added more recently. So let me go through this. Spanner uses something at Google called true time, which allows a extremely accurate time to be established at every server in every data center globally. And it uses global positioning satellites, GPS satellites, to achieve the true time service. And that's used to timestamp the transactions that are happening within Spanner. Because, as I mentioned earlier, the latency across data centers, if you're from within one region, in multiple availability zones within one region, would have a latency of 1 to 2 milliseconds, zone to zone or AZ to AZ. If you go region to region, it gets into 10, 20, 50, 100. Globally, it could be a couple hundred milliseconds. That would be completely unacceptable to have that kind of a delay for knowing exactly what time something happened in a database, in a distributed database system, right? That would just not work at all. Or it would require locking up the table for 100 milliseconds or something like that. It completely would not scale well at all. So this true time, which is based on GPS time signals, is how Google knows globally exactly what time it is at every Spanner server across the globe. That's really what makes the whole thing work. And compared to other distributed systems that we can imagine, like let's say Bigtable, for example, is distributed. It's not typically across regions, but it just is. In Bigtable, we have something called eventual consistency, or in lots of other distributed database systems, we have eventual consistency, but not fully ACID compliant. Okay, so it's a little bit more theory than I can go into here, but these are all live links. Anything in green is a live link. So there's, on the top, you have this the description of how Spanner uses true time, and then the second bullet is a research article from Google by Eric Brewer. Eric Brewer is the author of the so-called CAP theorem. CAP theorem says that you can, it talks about consistency models. So consistency, availability, and network partitioning. Network partitioning, P, means the division, like putting a fault between two servers in a distributed system that are supposed to be in communication. And the CAP theorem says typically you can only have 2 out of the 3. And in some of the books that I've referenced, like I think maybe in NoSQL Distilled, or maybe in 7 Databases in 7 Weeks, I forget which one of these books, I think they talk about the characteristics that the different databases have under the CAP theorem. So basically the idea is you can choose 2 out of the 3. So you can have C and A, but not P, and vice, something like that. So, and that's something you can Google for and search on. You'll have to, look up CAP theorem and understand the implications of that for the distributed system that you're choosing to run or choosing to build. Okay, but what I want to do is give you just a short quote from this Brewer article about Spanner. So Spanner and true time. So Spanner provides strong consistency for all transactions globally. Okay, implied there is the word globally. This is what's so unusual about Spanner. Strong consistency for all transactions. This combination of availability and consistency over the wide area is generally considered impossible due to the CAP theorem. Normally, if you choose availability and consistency, C and A, you therefore are not tolerant of P, of partitioning, and that's this wide area concept. So normally you can't have all 3. It appears that Spanner breaks that theorem or violates the theorem, but it does not do so because of this true time feature. So sorry, that's a lot. I wish I could go and explain it in full detail, and I've spent a fair chunk of time on that already, but that's the special ingredient that makes Spanner work the way it does, and that's what makes it globally available. And that ties into the exam questions as we've gone through some of the sample questions. Usually, if you see the word global, global consistency or something in that direction, you should be at least thinking that Spanner might be one of the options. I think we saw in one of our earlier questions that was not the answer that Google provided. We're not sure yet whether that was right or wrong, but that's what you should be thinking about. Now, the 2 lower bullet points I want to mention briefly are new innovations. Spanner has now been extended to have to store vector embeddings that are used with large language model applications, like basically generative AI applications that use retrieval augmented generation, or RAG. Part of RAG solution is that we take documents and chunk them up into pieces and make embeddings out of those chunks, and then store those embeddings in a database as a vector or a vector DB. Sometimes we use a separate vector database. There are several on the market. Most of the Google products are now being enabled to have their own vector databases, so that's being included in Spanner now. Spanner also has, when you use these vector databases to do similarity searches, so the idea is if you want to find documents that are similar to other documents, you look for vectors that have similar characteristics, and you do that by querying the vector database, which may have an index on it as well to assist in this. And Spanner now has both exact nearest neighbor and approximate nearest neighbor vector search to support Gen AI applications. That's new. Okay, that's something new this year. I think it's either in public preview or possibly in GA now. I'm not sure exactly where it is, but it's fairly new. It's quite new this year. Finally, there is, I mentioned earlier that Google didn't really have a graph database available among its database products. It now has added graph query language support to Spanner. Now, that's not going to be useful in every case because Spanner is a relatively expensive product at the low end. It's really made for larger volume, larger applications, and there is a minimum cost to running the smallest Spanner setup that you can have. And so you may want to have a graph query language, you may want to have graph support at a smaller scale, and maybe Spanner might be too expensive, but it's definitely a good thing to have and a good option to have, but just don't jump for joy yet until you look at the cost of it all. Okay, so just let you know about that. So that's enough for Spanner. So now let's move to Bigtable. So we had several labs on Bigtable, and what is Bigtable according to Google? And I've given you my take on it earlier at length, but Google's perspective is that it's a petabyte scale, fully managed NoSQL database service or use cases where low latency, random data access, scalability, and reliability are critical. And what I would add to that is that it's low latency both for reading and also for writing. So in other words, in most database systems, a heavy write load really impedes reading, and those two things are very much in competition. So it's a big challenge to maintain low latency reads in the face of high throughput writing, and that's what Bigtable is really good at. And so the example that comes to my mind is all the traffic sensors in a city. I think maybe it was San Diego. I don't know if it was is this from one of the labs. It may have been covered in one of the labs. It was definitely covered in one of the labs when I took it. I'm not sure it's currently in the lab anymore, but the idea is you have traffic sensors all over a big city. They're constantly, every time a car goes over a sensor, that event gets recorded. And so you have a lot of writing, and you also have the analytic reading back of that data to populate dashboards in the control center. So that's kind of the classic use case for Bigtable. The other thing is that it's fully managed. There is a cluster that you have to scale. You have to say how big your cluster is, and that controls your cost. So you have to make some choices there about how many resources to put onto Bigtable, and the cost does add up. And there is a minimum size cluster that costs a minimum amount of money per month. So it is, again, it's not completely serverless the way BigQuery is, but it is quite cost effective at scale. The other thing that's mentioned here is that Apache supports HBase API. It is often said that Bigtable works with the HBase API. What I tend to find a little curious is that actually Bigtable was created at Google first before Apache HBase, and HBase was developed using the ideas from the Bigtable paper that I referenced earlier. So people often say, oh yeah, Bigtable is Google's implementation of HBase, when it's actually the other way around. It's HBase followed the development of Bigtable, and that became an open source project. So it doesn't really matter as far as the API is concerned. I just think it's curious the way people state it. It's a great example of how a lot of fundamental research has come out of Google over many years and continues to do so, and many people don't appreciate that. Even today with OpenAI, the transformer model and the idea of embeddings came out of Google research that was published in 2017. Did not just spring from OpenAI last year or anything like that. So on the courses themselves, I would say, again, you have the course listing over here on the left, which is not particularly readable, but what is happening on the right here, I think the most important part of this is designing the schema and row key using Bigtable best practices. That's where you went into choosing a good row key. The row key is the only column that's indexed. All retrievals that are going to be done at scale must be done using the row key. You cannot do full table scans to find anything in the value part of the key value store, right? So you must use the key. And then again, joins are not possible in this system, or certainly not easy, unless you create some way on your own to do them, which I don't recommend. And then also the query language is not SQL according to these labs. In the future, it might include also SQL. So in other words, not only, what is it? Not only not SQL, it's no, SQL. I guess, I don't know where it is on the notation, but you get the idea. A couple of links down here for the advice on schema design and how to maintain the performance. So I think that is enough of Bigtable. We'll move now to AlloyDB. What's unique about AlloyDB is, so these are my slides. I pulled this from Google's documentation. The reason why I went to such length earlier today to explain the difference between a row store and a column store, because they support different use cases. AlloyDB brings them both together. It's really an amazing system in that way. It's unique among all database vendors for the way it does it. There are databases that go after the similar idea. They're called HTAP. And a good example, the so-called HTAP databases, and I am blanking right now on exactly what the HTAP stands for. Maybe somebody could look that up in the background, post that. It's HTAP. Somebody could look that up and post it in the chat. That would be great. A good example of HTAP database is SAP HANA. Okay, and they market the SAP HANA as probably the leading product in that HTAP space. I think HTAP might be a Gartner analyst term, or it could be, oh, thank you, right. So we're doing transactional and analytical processing. Fantastic. So that's what AlloyDB does. Now, SAP HANA, as maybe possibly self-appointed leader in the HTAP field, right? I think they are used typically an all-in-memory data store, and or at least it works. It's designed to work well when you have most of the data from the database in memory. Now, AlloyDB does not work that way. I don't think Google does not use the word HTAP to describe AlloyDB, but it is leaning in the same direction. In other words, you have a disk-based system now, but has both a row store for transactional workloads, and it's combined with a column store where you can define certain columns in the row store to have also a columnar storage. I want to be careful the way I use that word. So columnar storage, meaning a column store adjacent to the row store. And that, so what does that amount to? Let me go through the bullet points. Fully compatible with PostgreSQL. So you have flexibility and portability for your workloads. You saw in your labs, you saw two methods for migrating from PostgreSQL. It could be either a standalone Postgres instance, or it could be Cloud SQL Postgres version. You have a couple ways to migrate that to AlloyDB if you need it. You get, the benefit of that is you get 4 times faster performance for standard transactional workloads relative to Postgres. For analytic workloads, analytical queries, it's 100 times faster than standard Postgres. And I would say maybe 4 times of that comes from it being AlloyDB, and then the other 25, factor of 25, comes from the columnar data storage. So that's typically we see column stores are about 10 to 100 times faster than row stores for analytic queries. So that 25 falls right into the middle of the 10 to 100. So that's the benefit of having both the row store and the column store. That's, by the way, why it's called AlloyDB, because we're putting together 2 metals to make something better than we had before. I'll catch up to those chat window in a moment. So AlloyDB can also help you with a wide range of generative AI applications. Oh, sorry, I misread that. It's AlloyDB AI can help you with the Gen AI applications for the same reasons that I mentioned for Spanner, because it has the ability to store vectors and index vectors, and it also has the so-called scan algorithm, which is the scalable approximate nearest neighbors, SCANN, scalable approximate nearest neighbors. That's what Google is building into almost every database product that they have, including AlloyDB. That's what enables the RAG applications to work well with foundation models. Okay, finally, AlloyDB Omni is a downloadable edition that you can run on your desktop or laptop for experimentation. I've not yet tried it, but I'm planning to try it. And then I give you the clickable link there at the bottom. When you get the slides, you'll be able to click on that and check further details. Now, I would recommend, if you want to know more about this, the research note from Tony Baer is really excellent. This is not what I call trade press. This is really a high quality publication. Tony Baer is a really good analyst. I read this recently. This came out in 2022 when AlloyDB first came out. This is really very clearly well-written piece of research. It explains why AlloyDB is a better Postgres than Postgres. It's a better Postgres than AWS has Aurora, which is a similar kind of idea where it's it's an improved Postgres, an improved version of Postgres. And I think there might be other kinds of, I think Aurora might include also a MySQL variant as well. But there is a Postgres version of Aurora. Aurora is a great product, don't get me wrong. But what the point is that Tony Baer makes here is that Google has something very special in AlloyDB because the improvements in the transactional processing are somewhat comparable to AWS Aurora, but then you also have this addition of the column store, which makes the analytic queries really fly. And it's just really, this article is really clear. It's none of the problems that I pointed out earlier with other authors in other publications. So I highly recommend this. So the courses that we went through for AlloyDB are 6 courses, six courses, all labs. The ones that I think are the critically important one are 5 and 6, right? Number 5 especially is accelerating analytical queries using AlloyDB columnar engine. That's where you learn how to take the row store and add the column store alongside it to support the analytical queries, make them go 20 times faster than they would otherwise. And so if you've not gone through all of the labs yet and you're possibly running out of time, please do number 5 if you can at all. I think that's the most important one here. As always, the number 6 is a challenge lab, or often the last course, the last lab in a course is a challenge lab. That means you're not provided specific instructions. You have to go through and work out the details on your own. You often have to go through, pick up hints from the earlier labs will help you in the challenge lab. I think that that's it. I'm going to pause here for a moment to my air conditioner is making a lot of noise, so I want to see if I can stop that. Oh, I think it got better on its own. Well, I'll just turn it off. That solves that problem. Okay. We do have time for questions. Let me just jump ahead and see what else is coming up here. Right, it's just next step. So we're basically at the end. If there are, Jessica, have you been watching the chat? Is there anything? Thank you for posting about.
No, yeah, I've been watching. There's been no specific questions. Yeah.
Okay. I'm sorry, what's the bit about Snowflake?
People are just posting
links.
Oh,
I see.
There's no question.
I see.
The one question
examples,
that MA asks is, do you foresee a future where we are not using SQL? I actually don't.
Well,
I think SQL will be like the cockroach that survives.
I'm fairly close to retiring, so I'm definitely going to say no. For the rest of my working life, we will be using SQL. Definitely. Now, I will say that in specialized situations, there are cases where ODBC and JDBC drivers are not fast enough. I've seen a few of those cases, and I think sometimes API calls can be faster and have greater throughput for retrieving data. So it's possible, again, that other things may add to SQL. But, you know, SQL is such a funny language because it is both, it's criticized both for being too simple and simplistic. And so, well, you're not a real developer if you use SQL. You know, you're not, you know, you have to use Java or at least Python if you're going to be a developer, right? And that's just not true, obviously. And so it gets criticized from the hardcore developer community on that side. And then at the same time, some people say it's too complicated for data analysts and business people to learn. And I think to some extent, if it's getting criticized from both sides, maybe it's in the happy middle and it's really good for a lot of things, right? So I think it's not very hard for most analysts. Most analysts can learn basic SQL pretty quickly, and complex SQL takes more time. And so I'm thinking complex SQL is something in a warehouse where you're, writing ELT jobs that need to do a lot of processing. That's a little more challenging, but again, it's not that hard. And so I think that the reason it's going to be around forever is because it does occupy that middle space of being very powerful and yet relatively easy to learn for the basics. I don't know. Does anybody have different point of view on that? Oh, Teresa, do you want to say what you mean by dynamic SQL? Okay. Well, we'll leave it at that. Yeah. So low code, no code. That's a really good question about low code, no code. So I think that, so we see this in AI also, right, with Vertex AI, Model Garden, and all those things. We see no code, low code, and full on coding. And so the trade-off is that if you want full control over your models and best performance in training, you're going to have to learn enough AI to be able to build your own models, right? And so if that's beyond your capability, then you could try the low code, and probably the no code is going to be fairly limiting to the stock, the stock AI models that are there, not going to give you much flexibility. Now, the same thing happens in the data prep tools on Google. I don't know that I can remember all the names of the data prep tools right now. I don't know, Jessica, do you remember these? There's one called, there's one that's an implementation of, it's Trifacta product that is, I forgot what Google calls it in their managed service. So that's what I call.
Are you talking about, are you talking about Dataform?
Probably.
So what you're talking about, like, how do I describe it? Like SQL, I don't know that SQL orchestration is the right word, but
no, I
that's
don't
kind of
mean
how
that's
I think
Cloud
of. Okay.
Composer. I don't mean Composer.
No, that's scheduling.
Yeah.
Scheduling and orchestration are not the same thing. So like, I think you're talking about Dataform, like DBT.
Well, DBT is not a Google product. I'm thinking of the Google ETL tools, which is a little bit outside of this learning path, right? It's more properly in the data engineer learning path. But anyway, we can use it as an example. So Google has like low code, where low code and high code versions of ETL tools, right? So if you were a programmer, you would just jump in and use Dataflow, which is Apache Beam programming. So you program that in Python or Java, and you do your you specify your data transformations in that code. But if you're more of a business analyst, you could use one of the other low code tools that lets you profile the data, look at it, and do some transformations and then try it out. But it's typically a lower data volume, and it's probably less efficient, but it's easier for business analysts to use it. Do you remember what? You remember what that
Oh,
product is
I know
called?
what it's. Yep, yep,
Yeah.
yep, yep, yep. There are some people using it at our org. I will tell you, there's some gotchas because it is technically outside of the GCP environment. So
Okay.
from a security standpoint, no bueno. It really doesn't pass it. Data prep. There we go. Yeah.
Oh, thank you.
So
But it is labeled
yeah,
as a Google product, right?
it is a Google product, but it is not technically within the GCP. You effectively, it takes you outside of GCP when you like click on it.
Got it. Yeah, that it's the
Mm-hmm.
trifacta. Yeah, it's the trifacta
Mm-hmm.
product is the one I was thinking of. That's called data prep. Thanks for looking that up. That's an example of, low code versus higher code. I mean, a lot of Google products tend towards more code, I would say, because Google is such a strong Google has such a strong engineering culture, and they often tend to deliver a solution that requires a fair amount of coding. I know I've done. Jess, have you used DBT? You mentioned DBT. Have you? What's your experience with
So
that?
I know DBT, but the Google version of that is Dataform. Dataform was also a third party thing like DBT, and Google acquired it. And so now it's part of, specifically, it's a part of the BigQuery Studio now. So
Oh,
BigQuery
I
is
see.
not just BigQuery Studio. So it's like a whole suite of tools that are all integrated with
Yeah.
BigQuery. And so Dataform it's like one of the primary tools that I use and that I build for folks. It's what we're forcing all of like analytics and data science to now use so that they actually get version control on their stuff because they are very bad at
Right.
version control. Um,
Right.
like surprisingly bad. Probably one of the most shocking things to me when I got to like an enterprise software company, and I've asked other people who are at like Fangs and things like that. Probably one of the most surprising things to me when I got to an enterprise software company and like started out my customers are like analysts and people within the org. Um, and I would watch them troubleshoot like a query or something and like literally copying pasting code within a like going into GitHub and just
Yeah.
clicking on like the little edit button and like directly copying and pasting code like into like GitHub. I'm like, oh, I like died inside a little bit.
Into
So
copy back and forth between GitHub and the BigQuery console, in other words.
pretty much like no version
Yeah.
control, like just
Yeah.
like changing the code directly in GitHub or whatever. Yeah. Copying back and forth. Yeah. So Dataform connects to GitHub repo
Yeah.
or GitLab repo, any public repo. And so and then you can do the version control within the UI. So you don't need like command line. You don't need to like know Git, right? You just need to know the
Correct. Yeah.
buttons to push in the UI. And
Yeah, that
effectively,
was
it's
a
like
huge
how
it was a
we,
huge gap in BigQuery before that came out.
yeah. And so it effectively Dataform is like how you define like a data model, right? So lots of few or often many SQL queries that effectively build out a data model together, and then you can schedule it, like schedule Dataform tasks from Composer, which is Airflow. So these are the tools that we
Right.
kind of use together in our
Right.
pipelines. Because our like BigQuery houses like pretty much all of our data. Yeah. For Mailchimp. So yeah.
Yeah. So technically, what we're talking about here is not covered by this learning path because
Right.
Google has this somewhat artificial line between analytics and databases. So BigQuery is technically
Yeah.
on the analytics side, but it's
Mm-hmm.
very much the same idea. Um, I don't actually know how you would integrate Git with some of the database code in, let's say, Cloud SQL Postgres. How would you integrate that code with GitHub or something like that? I'm not sure how that would
Not
work.
really sure. They're doing all of that through like clusters and stuff. So
Yeah.
I'm not 100% sure. The news question is, are there any tools used to monitor databases live, like to check read and write throughputs or to identify hotspots and partitions? I think like the Google stuff, that Google monitoring has various metrics that you can track. You can set up for that, but I don't know
Yes, it does
more
for
specifics in
sure.
that. Yeah.
I'm not that familiar with them. Maybe I could look into that. Maybe we could discuss that next week.
Yeah, I think like Google monitoring and logging is for any of the Google products would be the way to go.
Yeah, I'll try to drill into that. So that was not covered really in any of the labs, I guess. Any of the labs that we did. Probably didn't go into that aspect of it. So I'll try to pull up a couple screenshots maybe for next week. How are people doing towards completing the labs? I mean, is there enough time left? Oh, Teresa, it looks like you're doing really well. So that's good. I know we had a few other people that were on joining most of our sessions, so I'm thinking that a few people have made good progress as well. The challenge labs are definitely tough. Some of them, especially the Oracle bare metal solution is that's not even a challenge, or I don't think that's a challenge lab, but it's one of the more difficult ones. A couple of challenge labs are pretty tough, yeah. Okay, seeing good progress here from at least a few people. So I think if there are not too many other questions, then I'll just move on through the wrap up, and then we can stay on and have a couple more questions at the end. Okay, thanks, Lawrence, for that comment. So we had, just to preview the rest of this. Yeah, as I showed earlier, we're in week of the formal sessions. This is the last one until we have the grand finale at week 11. So that'll be kind of a review of everything, maybe a little bit. Also some orientation toward the exam. We could do a few more sample questions. So did you do sample questions last week, Jess, or what happened with those?
Yeah, I did a few.
Okay, how did that go?
I did some. Well, I pulled some directly from the test questions, not from the ones that were already in the like pre-built lab, because I'm like, I don't like these. Seems to be a theme.
So
I tried to pull, yeah, and I pulled a couple from the practice exam, like that you do in the Google form, that were related to Spanner.
Okay.
You can see them if you look in the slide deck in our drive. Yeah.
I'll chat with you.
And I think it was fine. Yeah.
I'll chat with you afterwards about that. I wasn't sure exactly which slides you ended up presenting last week. So
the ones that were labeled as informal, yeah.
Okay.
They had the label on them. So okay. And I did like the Spanner and Bigtable things.
Okay, great. Now I know the ones that Google supplies as part of the sample question, the what do they call it? The not the ones that are in the slide decks, but the actual 20 questions that they give you for practice. Those actually have explanations with them. So we know what the right answers are, and they have the explanations to go along with them. So we're sure about those. Some of the ones in this slide decks, I think, were possibly not supplying always the right answer, or certainly, you know, 2 or 3 of us had some questions about that. So still might be a couple of unresolved issues on those. So let me go to, yeah, that's the end of the presentation today. When you get the deck, you can click on this link and get the badge. I think many of you have already done this. I think you only need to do it once, but oh, really? You're finding, Teresa, you're finding the AI labs are easier than the database labs? That's interesting. I wouldn't have guessed that, because I think overall, I think the MLE path is pretty difficult. And I guess my experience is that I had a lot of database experience before I took any of these. So for me, the database was relatively straightforward. Into those comments, though.